Okay, we will discuss some applications of uh, first order and second order differential equations having constant coefficients. So here, uh, one of the most important example of first order differential equation is the radioactive decay. Now here, in this phenomena, the radioactive substance decays with time, and the rate of the decay of that radioactive substance is directly proportional to the amount of the undecayed substance. So if dx is the if minus dx is the amount of the uh, decayed substance, and which is decayed in time dt, then we can say that minus dx dt is directly proportional to x, where x is the amount of the substance at time t. So amount of the substance present at time t, and x0 is the initial amount of the substance at t equal to 0. So we can write the equation as dx dt is equal to minus kx. So here k is the decay constant, and the minus sign indicates that the substance is decaying with time. So that is why this minus sign. So now uh, we can make a initial value problem and with this differential equation, and so when subjected to the initial condition is that x at t equal to 0 is equal to x0. So here you see that x is the dependent variable, and it is changing with time. So that is why the time is independent variable, and at when at t equal to 0, the value of the x is x0. This is the initial amount. So now we have to solve this initial value problem, and to calculate the expression of the x, that is the amount of the substance at time t. So now this now we are so we have to integrate this differential equation on both sides, and this c dash is the integration constant, and from this equation we get that this solution, which is x equal to c e to the power minus kt. So which is the general solution, because if the solution contains a parameter that is a constant, and this is a one parameter family of solutions, and so we have to find out the value of c using the initial condition. So the initial condition is at t equal to 0, this x is equal to x0. So so we get the value of c is equal to x0. This is the initial amount. So we can write the solution, that is a complete solution here, x equal to x0 e to the power minus kt. So the graphical representation of this equation is shown here, and you see that at t equal to 0, the initial amount is x0, and and this it is decaying with respect to this exponential function e to the power minus kt with time, e to the power minus kt. So the this k has a significance if now if the value of k is increased, so what will happen then, the rate of the decay will increase actually. So and mm, if now k is something a low value, then it will decay, that is the rate of the decay will decrease. So now from this calculation we can from this expression actually we can calculate the half-life, and the relation between this decay constant and the half-life. So the half-life is it is a time at which this x equal to x0 by 2. Now we will go to the next problem, which is some interesting problem in classical physics. That is, the body is falling under the influence of gravity only. this problem has two situations. The body is falling freely, that is in absence of any type of frictional force or viscous force, there is any kind of resistance force. And then the retarded fall, that is the body is falling uh, in presence of something frictional force or viscous force. So we will discuss the first situation, which is, that is a free fall uh, uh, of a body under the influence of gravity in absence of any kind of resistance force. So that is, we are not discussing any kind of resistance in the motion. So this body is falling from a height, suppose h, with respect to some uh, uh, any any value of height, and it is from rest, and we we consider this a xy coordinate system, and this, the origin of the coordinate system is here, the where the body, that is the object, is situated. So so we can write the equation of motion as m d2y dt2 is equal to mg. Now you see that this body is moving down and along the y-axis, and here x is constant, and it is moving down under the influence of the gravitational force, gravity, that is the mg. And so here the variable, that is the dependent variable is y, and it is changing with respect to the time. So we can say that y equal to y function of time. So here y function of time. So this mass into acceleration is the force due to inertia or due to this mass m, and which is equal to the force due to gravity, that is mg. So from this equation of motion, we can write d2y dt2 is equal to g. Now it is a second order differential equation. Now from this second order differential equation, we can obtain a first order differential equation if we change the variable as that is y to b. We know that this d2y dt2, this acceleration is equal to the dv by dt. So this is the first order derivative of the velocity. So from this so this is a first order differential equation, and we can get the expression of the velocity here. And also, and if from this second order differential equation, we have to solve for two constant c1 and c2, and then we have to find out the value of the y, that is the distance of the body from that origin. So here in this problem, we have to calculate the position after time t, or we can say there is the distance of the object from this origin o. So from this situation, and from the differential equation, we can make a initial value problem with this differential equation, that is d2y dt2 is equal to g. And when subjected to the initial condition, that is y at t equal to 0 is equal to 0. So the initial position is 0 because the body or that object is situated at the origin, that is why y equal to 0 at t equal to 0. And now it is falling from the rest, that is why the initial velocity, that is y dot at t equal to 0 is equal to 0. So this age is not needed actually. And now now we have to solve this initial value problem to calculate the distance of the object, then, which is y. So these are simple steps, and we have to integrate both sides of this equation, and we get this uh, equation for the first order derivative of y, that is the velocity. And this is the first constant of integration now here. And we can get the value of c1 using the initial condition. So here at t equal to 0, we know that dy dt is equal to 0, so c1 equal to 0. Now putting this value into that equation, and we get that dy dt is equal to gt. So again integrating to get the expression of y, which is y equal to half of gt square plus ct c2. Now at t equal to 0, y equal to 0, then we can write that c2 equal to 0. That's why y equal to half gt square. So this is the expression of the y. So this is the expression, that is y equal to half gt square. Now we can obtain the value of the velocity by differentiating with respect to time. Now we will consider the retarded fall. The retarded fall means the object, that is the body, is moving down now in presence of some resistance. So here resistance, that means some frictional force or viscous force. So this frictional force or viscous force is arising in due to the presence of air medium actually. And in this situation we can write the equation of motion as m d2 by dt2 is equal to mg plus fr, some retarding or resisting force. So here the equation of motion is the differential equation uh, uh, for the equation of differential equation of this problem. So this resisting force can be written as f, this fr is equal to minus ry dot. So this resistance force depends on the velocity of that object. So we know that from the Stokes law, that is the viscous force acting on a spherical object of radius r is equal to 6 pi eta rv. When the body, that is a spherical object, is moving through a viscous medium with a speed not so large. So when so in this situation, that is the viscous force acting on that spherical object, we know that f equal to 6 pi eta rv. So here v is the velocity of that object, and r is the radius of that spherical object, and eta is the viscosity, coefficient of viscosity, and 6 pi is the constant. So you see that the force is proportional to the velocity of that particle. So uh, this is valid only for a small object, a spherical object, and for a low velocity. And so uh, so in this situation we can write this retarding force, that is the resisting force, or you can say the frictional or viscous force is minus r into y dot. So here minus r, that means it is directed opposite to uh, the uh, direction of motion of that particle. So but that is why it is here minus. And if the speed increases, then we can say this resistance force increases, that is it resists more. So that is why this minus sign here. So now we get this differential equation m d2 by dt2 equal to mg minus r dy dt, and now dividing both sides by the mass, we get that d2 by dt2 is equal to g minus r by m dy dt. So here minus say here this r by m is now written in terms of this another constant gamma. So the differential equation is this. Now the initial value problem, we can make this differential equation when subjected to the initial conditions, that is y is equal to 0 and at t equal to 0, and y dot, that is the velocity, is 0 at t equal to 0. So this differential equation is a non-homogeneous differential equation, and the reduced form of this non-homogeneous differential equation can be solved using a trial solution y equal to the alpha t, and we know that how to solve this equation. And we have to we have to find out the roots of this auxiliary equation, that is alpha square plus gamma alpha equal to 0, and the roots are alpha equal to 0 and minus gamma. So from this calculation, we find out the value of the complementary function, that is the solution of the reduced equation, and that is y is equal to c1 plus c2 e to the power minus gamma t. And now we have to find out the particular solution. So the particular solution can be um, calculated some using the operator method of solving non-homogeneous differential equation. And you see this differential equation is written in operator form. So d square plus gamma d operating on y is equal to g, and from this equation we get that yp equal to 1 by d square plus gamma d operating on g. Now writing this term, this operator term, in partial fraction. So in partial fraction, this can be written as 1 by gamma 1 by d minus 1 by d plus gamma operating on g. And after few steps we get the value of yp is gt by gamma minus g by gamma square. So the complete solution of that non-homogeneous differential equation is y equal to c1 plus c2 e to the power minus gamma t plus gt by gamma minus g by gamma square. Now from this equation we have to calculate the derivative, that is y dot is equal to this. And now we have to put the initial conditions to find out the value of c1 and c2. So for this equation at t equal to 0, we know that y equal to 0, that's why this c1 plus c2 minus g by gamma square equal to 0. And from this expression, that is the expression of the velocity at t equal to 0, that is y dot equal to 0, then we get c2 equal to minus c2 equal to g by gamma square. So c2 equal to g by gamma square, and putting this value of c2 into that equation of c1 plus c2 minus g by gamma square equal to 0, and we get that c1 equal to 0. So c1 equal to 0 and c2 equal to g by gamma square. So the complete expression of the solution is y equal to g by gamma square into 1 minus e to the power minus gamma t plus gt by gamma. So this is the expression of y, and from the expression we can calculate the distance of that object from the origin uh, for some time t. So if we know the value of gamma and t and g, so we can calculate the value of the y. So from this expression we can get the expression of the velocity v, which is v equal to g by gamma into 1 minus e to the power minus gamma t. So one interesting situation in this case is that as the body is falling under the influence of gravity and in presence of the uh, air resistance, that is uh, from frictional uh, force. So you see that after a long time, that is when we if we consider that at t equal to infinity, then you see that this velocity become constant, that is v equal to g by gamma. So at t equal to infinity, this term uh, is uh, is 0, so we can write v equal to g by gamma. So this is a constant velocity. So after a long time, this object attains a steady velocity or a constant velocity, and this velocity is said to be a terminal velocity. So now another interesting problem of in classical mechanics is the simple harmonic oscillator. So we will see the solutions of the differential equations by getting from this from this system. So we will consider the simple harmonic oscillator, which is one dimensional, that is it is oscillating along a specified direction, suppose it is x. So this system is a spring mass system. The oscillatory system is the spring mass. So one end of this spring is connected to a fixed end, to a fixed object, and the another end of the spring is connected to a mass, that is a object of mass m. So initially this we consider that this spring and this mass which is at this mass is actually oscillating with respect to some a fixed position, and that fixed position is the equilibrium position. So we say that at initially this mass is at the equilibrium position. So from in this position, that is the spring and the mass is at rest and it is not moving. So now if this spring is stretched, in this figure b you see stretched up to some point p, that is the this mass is pulled aside up to this point p, uh, from that equilibrium position o, which is at x equal to 0, and the distance of that point p from that equilibrium position or the origin is x equal to a. So now what will happen? So if it is released from this point p, then this mass will oscillate with respect to this equilibrium position x equal to 0. So it will oscillate because of that spring. So this spring actually it restores back to that initial position, that is the equilibrium position. So this spring exerts a force on that mass, uh, uh, because of its stiffness, and the stiffness constant of the spring, that is represented by the k. So the restoring force will depend on that the stiffness constant of the spring. So so how much it will oscillate, it will depend on the stiffness constant of the spring and also the mass of this object. So that is the frequency of oscillation will depend on both the mass and the spring constant k. So now so we have to uh, so we have to calculate so we have to give uh, the expression of the differential equation uh, in, in this situation, that is in this oscillatory motion. So so you see that it is this mass is displaced from that origin, that is x at x equal to 0, and we can say that x is the displacement. So here the displacement is 0 at the equilibrium position, and we say the displacement, that is x is equal to a at this position. So we can say this x is a dependent variable and it is a function of time t. So now the differential equation would be this mass into acceleration, that is acceleration along this x-axis. This is equal to the restoring force, this restoring force which is exerted on that mass m due to this spring. So and now these two forces are equal and opposite, because this restoring force we know this is equal to minus kx. The minus sign indicates that uh, it is directed that is it is opposite to the uh, direction of motion, or opposite to the displacement. When it is displaced along the positive axis, then this spring exerts a restoring force on that object uh, 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 to the minus x-axis. So restoring force is acting opposite to the motion, that is opposite to the displacement actually. And so and this k is the stiffness constant or the spring constant of this spring. So now we will consider that the displacement of the object from that equilibrium position or the rest position, we say that this is the maximum displacement, that is x equal to a. This is the maximum displacement, and now it is released uh, at t equal to 0. So we consider that at t equal to 0, initially the mass is at the maximum position, maximum displacement, and then it is released from the rest. So the differential equation is this: m d2x dt2 is equal to fx fs, or m d2x dt2 is equal to minus kx. And and from this differential equation we write that d2x dt2 plus omega 0 square x equal to 0. So here omega 0 is equal to root over k by m, and you can see this this is an expression of a simple harmonic motion. You know already this, and this is the natural frequency of that system, and this natural frequency, or you can say the angular frequency, omega 0 is equal to root over k by m. So in this way, this frequency depends on the spring constant and the mass. If the mass increases, then the frequency decreases. And now we have to so from this situation, from this differential equation, we can make initial value problem, and when subjected to this initial condition, that is x at t equal to 0 is equal to a, that is at t equal to 0 the displacement is maximum, which is a, and the initial velocity is 0. So now this differential equation is a homogeneous differential equation, and we can solve this using a trial solution, that is x equal to e to the power alpha t. So here this is this is similar to the previous problem, and you can see this alpha, this auxiliary equation has two roots, and these two roots are I omega 0 and minus I omega 0. The roots are complex and distinct, so we can write this general solution of that homogeneous differential equation as x equal to c1 cos omega 0 t plus c2 sin omega 0 t. And now taking a derivative with respect to time to get the velocity of that expression, there is x dot is equal to minus c1 omega 0 sin omega 0 t plus c2 omega 0 cos omega 0 t. Now from the velocity expression, first calculating the expression value of c2, we know that this initial velocity is equal to 0, that is x dot at t equal to 0 is equal to 0. And so then we see that this is c2 equal to 0. Now so c2 equal to 0, and putting this value of c2 here, so we get x equal to c1 cos omega 0 t. So x equal to c1 cos omega 0 t, and now we have to find out the value of c1 using the initial condition for x at t equal to 0 initially, which is the maximum. This is a, so c1 equal to a. So we get the expression of the displacement here, x equal to a cos omega 0 t. So the graphical representation of this equation is shown here. You can see this is a cosine function of t, and you see the oscillation, and the maximum displacement, this is equal to x equal to a. Suppose sorry, this is omega t with respect to x is plotting with respect to omega t. So you see that maximum displacement occurs at omega t at equal to 0, that is at t equal to 0. So when omega t is equal to pi by 2, then you see this x equal to 0. So omega t at pi by 2, you can see that x equal to 0. Now let's see what will happen in the velocity. So the velocity is we can calculate from this expression, this xd, that is v equal to minus a omega sin omega 0 t. Sorry, this is omega 0. So now you can see that at omega 0 t equal to pi by 2, you see this is minus omega 0. So it is a maximum in the negative direction, that is here this is minus omega 0. So we can say that when the displacement is maximum, so here this maximum, this is 0, then velocity is 0, and when displacement is 0, and you see the velocity is maximum. So when the displacement is 0, the displacement is 0 in the equilibrium position, because it is oscillating with respect to the equilibrium position. This is the equilibrium position. So in equilibrium position, the displacement is 0, but the velocity is maximum. but and when the displacement is maximum at this position p, the velocity is 0. So both the velocity and position cannot be maximum simultaneously at the same time. So here omega, so you can see that this a, this is the amplitude of the oscillation, and this is the displacement, and omega 0 is the angular frequency, so that we can calculate the time period is equal to 2 pi by omega 0. This is 2 pi root over m by k. So this is the time period of oscillation. Okay, now we will consider the damped harmonic oscillator. So but the damped harmonic oscillator is the simple harmonic oscillator in presence of some damping force. So damping force, that means some air damping. So this is so this is the situation similar to the retarded fall of a body in under the influence of gravity in presence of frictional force. So in this case, mm, some resisting force or the damping force will be present, and we know that this f of r, this is equal to minus rx dot. So the equation of motion here, m d2x dt2 is equal to minus kx minus rx dot. And now the same the differential equation is different, but with an extra term, that is minus rx dot, and but the initial conditions are the same. That is the initial that is a displacement initially at t equal to 0 is equal to a, and the initial velocity is equal to 0. From this differential equation, we write this d2x dt2 plus omega 0 square x plus gamma dx dt equal to 0. So here gamma is equal to root over r by m. So now this is a homogeneous differential equation, and it can be solved using this trial solution, which is x equal to t to the power alpha t. And in the auxiliary equation has two roots. These are minus gamma plus root over gamma square minus 4 omega 0 square by 2, and minus gamma minus root over gamma square minus 4 omega 0 square by 2. So alpha 1, writing this term there as omega equal to root over gamma square minus 4 omega 0 square by 2. So we can write alpha 1 alpha 2 is equal to minus gamma by 2 plus minus omega. Now depending on the values of this gamma and 4 omega, so uh, we can go to three different situations. So if this gamma square is larger than this value 4 omega 0 square, that means this gamma, that means the damping term, damping constant, the damping constant is very high compared to the omega 0. So how is omega 0? Omega 0 depends on the spring constant. So damping term is very high compared to the the restoring force actually. So stiffness of the spring. So we can say that this in this case the roots are unequal, and we can write the solution as x equal to c1 e to the power minus gamma by 2 plus omega into t plus c2 into e to the power minus gamma by 2 minus omega into t. And now you see this expression, and you can easily understand that there is no oscillation at all, and this situation is said to be a over damped motion. So it is over damped, so that is why it will not oscillate. The mass will not oscillate with respect to that position. Actually the motion will be decayed very fast as the damping is very high. The damping, that means the resistance is very high. And now we will consider the situation when gamma square is equal to 4 omega 0 square. So the roots are equal, and for in this case we can write the displacement as x equal to c1 plus c2 into t e to the minus gamma t by 2. Again there is no oscillation at all, and this situation is said to be critically damped motion. Again in this case the system, that is the mass of that oscillator will not oscillate, so it will decay very fast with respect to time. And now the interesting situation is when gamma square is very less than 4 omega 0 square, and this situation is said to be an under damped motion. This is called an under damped motion situation. So in this underdamped motion, the roots you see this are uh, unequal, and they are complex. So one root is alpha 1 is minus gamma by 2 plus I omega, and alpha 2 is equal to minus gamma by 2 minus I omega. So we can write the expression of x as x equal to e to the minus gamma t by 2 into c1 cos omega t plus c2 sin omega t. Now c1 c2 can be find out using the initial conditions, and these are simple steps. I am not going through all the steps. So and you can easily calculate the value of c2 and c1. So and you can see that c1 is equal to a and c2 equal to gamma by 2 omega. So this x equal to the minus gamma t by 2, this is a cos omega t plus a gamma by 2 omega sin omega t. So easy calculation of that constants. And now in this expression I'm writing this term, this cos omega t into 1. So 1 is written in terms of some another constant, that is cos alpha is equal to 1, and this gamma by 2 omega is written in terms of a sin alpha, that is sin alpha equal to gamma by 2 omega. So this is a x equal to e to the minus gamma t by 2. So we can write that this cos alpha cos omega t plus sin alpha sin omega t. So this can be written as cos of omega t minus alpha. So now the interesting theory is that you see the expression of the displacement in damped harmonic oscillator is x equal to a e to the power minus gamma t by 2 into cos of omega t minus alpha. And we know for a simple harmonic motion this is x equal to a e to the power minus gamma t by 2 into for a simple harmonic motion we know that x equal to a cos omega t. So so the difference is that in this case, in this expression, actually the amplitude is a into e to the minus gamma t by 2. So there is a exponential term in the amplitude of this expression, and there is a phase difference, that is alpha. So what will happen in this situation? The graphical representation of this equation is shown here, and you see this amplitudes, the amplitude is not constant here. In this situation, for a damped harmonic oscillator, the amplitude decays. The amplitude decays with respect to this term e to the minus gamma t by 2. So uh, so but there is also the oscillation, but the oscillation decays with respect to this exponential term. So for a simple harmonic motion, there is a oscillation with time, the amplitude is constant. But for a underdamped motion, underdamped harmonic oscillator, the oscillation decays exponentially. Okay, and now we are going to the next problem, the third situation of that simple harmonic oscillator, when the simple harmonic oscillator is subjected to a external force, and the force is a periodic force, and we will consider the damped harmonic oscillator. So the next problem is the forced damped harmonic oscillator. The damped harmonic oscillations in presence of an external periodic force, that is this is F equal to F0 cos omega t. So here omega is the frequency of that periodic force, external periodic force, and the differential equation can be written as md2 x dt2 equal to minus kx, this is the restoring force due to the spring, minus rs dot, this is the damping force due to the friction, and this f0 cos omega t is the external force. And the left hand side term is the force due to inertia, so they are equal. So now we get a non-homogeneous differential equation. So this is the non-homogeneous differential equation, which is d2x dt2 plus omega 0 square x plus gamma dx dt is equal to f0 by m cos omega t. So we know the complementary function, that is a solution of the reduced form of this non-homogeneous differential equation, that is x equal to c1 e to the power minus gamma plus and so on this term. And now we are considering the underdamped motion, so that we can write the complementary function as x equal to a e to the minus gamma t by 2 cos of root over gamma square minus omega 0 square by 2 into t minus alpha. So that is under that motion. This complementary function is in underdamped motion where gamma square is less than omega 0 square. So now we have to calculate the particular solution of this non-homogeneous differential equation, and before that we have to write this differential equation in operator form. So we see that the expression is d square plus gamma d plus omega 0 square operating on x is equal to f0 by m cos omega t. So so the expression of the particular solution xp is equal to 1 by root over d square plus gamma d plus omega 0 square operating on f0 by m cos omega t. So we know the technique of solving for this type of function, and this cosine function first converted into the exponential form, and then we are writing in this way, is that is 1 by this operator operating on e to the power I gamma t, and the same operator plus the same operator operating on e to the power minus I gamma t. So now we know that in this case, when the function is exponential form, and the and here this operator is a polynomial function of d, then this d is replaced by the coefficient after the time in the exponential term. So d is replaced by I omega, so we get the expression is this. Similarly for this operator also, and after a few calculation we get the expression, that is the xp equal to f0 by omega, which is omega 0 square minus omega square by omega 0 square minus omega square to the power square minus gamma square omega square into cos omega t plus this term. And now writing this term, there is f0 by omega into omega 0 square minus omega square by omega 0 square minus omega square to the power square minus gamma square omega square. So this term is written as c cos phi, and f0 by omega into this term, the coefficient of sine omega t, is written as c sin phi. So from these two expression, and we can write this phi equal to tan inverse gamma omega by omega 0 square minus omega square. And if you put this expression of c cos phi and c sin phi there, so this expression can be written as xp equal to c cos of omega t minus phi. So the complete solution we get is this x equal to a e to the minus gamma t by 2 into cos of this in t into minus alpha plus c cos omega t minus phi. So so this is the complete solution. Now, so we are not getting any idea about what will be the situation practically in presence of that external periodic force. So now we are concerned about the situation, that is the motion after a long time, when this t is at tends to infinity. So so after a long time, you see this term is 0. So v to the minus gamma t by 2 is 0 at t tends to infinity, then this term is 0. So you see that x equal to c cos omega t minus phi. So x equal to c cos omega t minus phi, and you see this is this is again a simple harmonic oscillation. So and this is said to be a steady state motion, because in this case you see the motion will be a steady state, and yeah, and the displacement, actually then the system oscillates with the frequency of the periodic force, but with a phase difference phi. So if the force suppose this is the force external force which is oscillating with frequency omega, and then what will happen, then the oscillator also, it will oscillate with respect to suppose we will oscillate with respect to that same frequency, but with the phase difference. That is why I'm writing in this way, same frequency, same frequency. So the in the steady state motion, that is, motion will be steady after a long time at t tends to, sorry, this is infinity, tends to t tends to infinity, then x equal to 0, the complementary function is 0, and we see that x equal to c cos omega t minus phi. So in this situation, that is the steady state motion, the displacement, that is the of the simple harmonic oscillator oscillates with the frequency omega, but that is that is with the frequency of the periodic force, external periodic force, and external periodic force. But the oscillator oscillates also with the period with the frequency omega, but with the phase difference, that is phi. So these are the applications of the differential equations, second order differential equations having constant coefficients in classical mechanics. There are also some good examples of differential equation uh, in LCR circuit, CR circuit, and also LR circuit. So in electric circuit also, we can calculate, that is, we can create a differential equation, and after solving those differential equation, we can calculate the value of the current or charge in the electric circuit. Thank you.